Hey, what's up guys? This is Dr. Vivek Palepuram bringing you the next lecturette in ECPE 170 MIPS assembly. In this lecturette, I cover some working examples on the use of memory instructions in MIPS assembly. Before we proceed any further, I think it's a good idea to revise the array concepts and how your C program views an array. The very first important concept with respect to arrays is that the name of the array is the address of the very first element. That's one of the most important concepts. So if you were to printf, array is going to print the address of the very first element. The next important concept is that the values are spaced by the size of the data. For example, integers have size equal to 4 bytes. So integers will be placed by 4 bytes, or they will be spaced by 4 bytes inside of the main memory. So for example, consider this C code for instance. Let's say that I have an integer array. If I were to print the address of the very first element, let's say that it prints 65530 for some reason. Then the address of the next element, array of 1, is going to be 65534. So array of 0 and array of 1, they are spaced by 4 bytes. And similarly, the contiguous values are spaced by 4 bytes because my data type is integer whose size is 4 bytes. So array of 1 will have address 65534. Array of 2 is going to have the address 65538. Similarly, doubles are spaced by 8 bytes. In your C programs, you have used base offset addressing and indexed addressing to access different array values. A of 5 is an example of base offset addressing, whereas array of I is an example of indexed addressing. Now let's see what happens when we access an array element using base offset addressing. Let's assume that for some reason, the array A in your C code is mapped into the main memory, something like this, meaning the first element has address 10, the next element has address 14, then 18, then 22, and so on and so forth. When you specify A of 5, here's what compiler is going to do. Compiler is going to consider the name of the array A as the base address. Whatever offset you specify here, 5 in this case, that will be multiplied by the size of the data type, which is integer here. So the size of the data type is 4. So this offset value 5 will be multiplied with 4, giving you a value 20. Then the newly computed offset in bytes will be added to the base address, 10 in this case, to get you the address of the target element, which is 30. So 30 is the address of A of 5. And you can use this address to query the value at A of 5. Pointer arithmetic is also one of the useful methods of accessing different array elements. This is an example of how you can use pointers to access array elements. Consider this printf statement for instance, and specifically notice how I am trying to access A of 5 using pointer arithmetic. Array is your base address. When you add 5 to the base address, your compiler is going to perform arithmetic with respect to the size of the data type, integer in this case. So when you add 5 to the base address, it's going to multiply 5 with 4, giving you 20, because 4 is the size of an integer. That 20, the newly computed offset in bytes, is going to be added to the base address, giving you the address of the target location. Then you use this asterisk symbol as a key to unlock the value at that address. So that is an example of how you can use pointer arithmetic in order to access array elements. Now, this pointer arithmetic concept will be quite useful when we consider MIPS programs and when we try to access our arrays in MIPS programs. Okay. Now here's what I would like for you guys to do. I would like for you guys to work on problem 2, arrays revisited. So here, what you need to do is write a simple C for loop to print the values of a 1D array using these methods. So indexed addressing and pointer arithmetic. Before you start working on this problem, let me give you my solution, which will be a kind of hybrid between, or rather a cross of indexed addressing and pointer arithmetic. So let me give you my solution. Now your solution has to be different than mine. Let's say that I declare an integer pointer int asterisk IPTR. Further assume that array has already been declared elsewhere. Now notice how I'm going to set up my for loop and how I am going to access or print the array values. So I'll set up my for loop for I is equal to 0, I is less than n, I plus plus. Inside of this for loop, I'll set IPTR to array plus I. So I am obtaining explicitly the address of the target element that I'm trying to access. And then in the next line, I'm going to execute this printf statement, which is going to use the base offset addressing mode. So using IPTR, I explicitly obtain the address of the target element. And then once I arrive at that target element, I use the offset equal to 0 to access the array value. So this method is going to have some implication on how you access array elements in MIPS using a for loop. So please go through this for loop one more time. You can pause your video here and take your time and go through this for loop and make sure that you understand this for loop. Once you're done, you can work on this problem. You can pause your video, work on this problem, and once you're done, you can unpause it and we can move on. All right, guys, so let's move on and try to use our LW and SW instructions that we acquired from our previous class to this particular problem. So here I have a nice register map, which is going to be quite instructive for me. It's going to tell me how different registers are used and for which variables these registers are used. So register S1 is for G, H is S2, and the base address of the array is stored in S3. Let's say that this is our pre-constructed register map. Now also assume that somehow we have already acquired the address of the base or the base address of the array, which is in S3. I'm going to give you specific instructions as to how to obtain the base addresses, but that's for some future slides. Here, let's assume that S3 is already set. For this computation, I need to obtain array of 16 first. So let's obtain array of 16 into a temporary register. Let's use T0 in this case. So I can do something like this. I need to load a value from the memory. So I'll use LW instruction, load word to $T0. S3 is my base address, 16. So now T0 holds the value, and then I need to add this T0 value to H and store the result in G. So I can do something like this, add, store the result in S1, the H, which is S2, comma, T0. Now let me ask you this question. If array were an array of integers, would this work? It's given to you that array is an array of words. So will this work? You can pause your video here and tell me whether this code is right or wrong. As it turns out, the code that I wrote is incorrect. It has a slight flaw. Well, in my opinion, it has a major flaw in it, in that we did not appropriately obtain the correct address of the element that we are looking for. Now remember, if your array is an integer array, each of these integers will be spaced by 4 bytes. So first we need to explicitly calculate the offset in bytes by multiplying the offset number with the size of the data type here. Meaning we have to multiply 4 to the offset that we are trying to use in our code. So let me work this example one more time correctly. So still, I'm going to use T0 register to get the value of array of 16. Now, because elements are spaced by 4 bytes, so array of 16 will be at an offset of 16 times 4, which is equal to 64 bytes. So I'm going to use this as an offset, 64, followed by the base address in parentheses. Now that I have obtained the value in T0, I can perform add to $S1, which is G, $S2, comma, $T0. So this is the correct method of accessing elements. What you need to do first is you need to properly multiply the offset with the size of the data type and then use the newly computed offset in bytes to access the array elements. So MIPS follows this method. MIPS follows this base offset method. You need to explicitly calculate offset in bytes and then use the base address. So you need to obtain offset in bytes first. Always remember that. So let's draw a comparison between how you have been accessing arrays in C and how you will access arrays in MIPS. C has this very familiar format. You have your base, then in square brackets you specify the offset that you would like to access. Now your GCC compiler is going to implicitly multiply this offset value with 4 to calculate the offset in bytes. Then it's going to add it to the base address in order to point to the address, or in order to point to the value that you're trying to access in your C program. So C compiler is going to multiply that offset for you with the size of the data. MIPS programs, however, this is how you're going to access different array locations. So in parentheses, you're going to specify the base address, which is going to be stored in one of the registers. And the choice of the register is totally up to you. Offset needs to be in bytes and it has to be pre-computed. It has to be pre-computed properly by the programmer. So in MIPS programs, you are going to multiply the offset with the size of the data to compute the correct offset in bytes. I cannot stress this point anymore. This is really very important point. Now let me give you a fun example as to how your C program views arrays and how your MIPS programs view arrays. So let's say that we are first going to see how a C program is going to view arrays. Let's say that you are in a city with blocks. So you have block 0 here, you have block 1, you have block 2, and you have block 3. And further, let's say that you're currently at block 0. And let's say that you were to ask a person who's sitting in block 0, where is block 3? Then the person sitting here in block 0 is going to answer 3 blocks down the lane. So happily, you are going to skip 3 blocks and arrive at your target location. That's how your C program works. Now let's consider MIPS programs now. So let's consider how your MIPS program is going to view these array values. In your MIPS programs, things are a little bit different. Let's say that you have these lanes that have this lane that has certain steps, and further assume that each of these blocks occupies 4 steps like this. So this block has step 1, 2, 3, 4. This one has 1, 2, 3, 4. This one has 1, 2, 3, 4. So each of these blocks has 4 steps. Now, if you were standing in block 0 and if you were to ask where is 3 of block, then your MIPS program here is going to tell you take 3 steps down the lane. Instead of 3 blocks down the lane, it's going to ask you to take 3 steps down the lane. So you will take 3 steps, 1, 2, 3, and you will find that you are still not at your target location. So you as a programmer will have to explicitly multiply the number of steps taken for each block, 4 in this case, with the offset that you're specifying. So you need to multiply 3 with 4, giving you 12. So you'll skip 12 steps. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then you would arrive at your target location. This is one of the most important aspects with respect to accessing array elements in MIPS. Oftentimes, programmers forget to multiply the offset with the size of the data type, and as a result, their program breaks most of the time. So I hope you'll use the simple example and remember that you need to obtain proper offsets in bytes. All right, now let's work on problem number 3. What you can do here at this point, you can pause your video and try to solve problem 3 on your own, and then I'm going to give you the solution once you're ready, at which point you can unpause your video. Okay, so let's work on this problem. So I need to perform h plus array of 8 and then store the value, the answer, at array of 12. So first things first, I need to get array of 8. So let's use base offset addressing to get the value array of 8. So I'm going to use the register T0 for that. So load word into T0. $S3 is the base address. Let me ask you this question. What will be the offset? Will it be 8 or will it be 32? The answer is 32 because I need to multiply 8 with the size of the data type, which is 4 bytes. So 32 is the correct offset. So now I have obtained the value that is stored at array of 8. Next, I need to add it to H. So H is S2 register. So let me use another register T1 to store the result of this addition operation. Add to $T1 H, which is S2, comma $T0. Next, I need to store the result, which is in T1, to this array location. So again, I need to use base offset addressing to store a value at array of 12. So store word $T1, base address is $S3. Now my offset value is 12 times 4, which is equal to 48. So that's the solution for this problem, problem number 3. Now let's work on problem number 4. This kind of C statements you will often find when you are executing some sort of a for loop or a while loop or any kind of loop where I is going to increment or decrement. So you can pause your video here and try to solve this problem on your own. Specifically, what I would like for you guys to do is recall that hybrid indexed base offset addressing method of printing the array values that I showed you earlier. So what I did earlier, I declared an integer pointer IPTR. Then inside of the for loop, I obtained the explicit address of array of I like this. And then I accessed the array value using base offset addressing IPTR of 0. This method will be quite useful to convert this C code into MIPS. So you can pause your video and try to solve it on your own. I encourage you to do that. Okay, so I hope you guys got the chance to solve this problem. So again, I need to perform this addition operation. So first I need to get array of I. Now remember, when you are using base offset addressing, the offset always has to be a constant. Offset is always a constant when you use base offset method. So here, what I need to do is explicitly first arrive at this location array plus I, and then I can use the 0 as my offset to get the value which is at array of I. So let's do that. First, I need to calculate the offset in bytes appropriately. So I need to obtain 4 times I. Now, carefully notice here that I'm not going to modify I. So you should not try to modify I in pursuit of obtaining the offset in bytes. You need to use some other register here. You should not modify I when you try to compute the offset. So let me use a register T0. So add to $T0, $S4, $S4. So using this step, I would have computed 2 times I. Next, I'm going to add T0 to itself and store the result back in T0. So now I would have obtained 4 times I. Now, if you remember, I did not introduce you to a mul instruction just yet. I am still using all the simple instructions that I have given you so far, just the handful of instructions to perform all kinds of operation. So now I have my proper offset in bytes stored in T0. Next, I'm going to explicitly obtain this address array plus I. So I will use the base address, which is S4, add this newly computed offset to it. I can reuse T0 register and place the address of the target location back in T0. So now T0 holds the address of array of I. So that is this step right here in your C program. Next, I'm going to use the base offset method of obtaining the value from this location. So let me use T1 register for that. So load word, load into T1, 0 is the offset because I am at my target location. And in parentheses, I have $T0, which is the address. Now remember guys, address is always going to be a huge value. So whenever you perform your MIPS executions using the simulator, carefully notice what are the values of these different registers. If for some reason T0 is a small value, then something has gotten wrong, which tells you that your program is going to break. More on the simulator later. Okay, so now I have obtained T1, or rather I have obtained array of I inside of T1. I need to add it to H and store the result to G. So I'm going to do add, store the result in S1, H, which is S2, comma, $T1. So that is the solution for problem number 4. You can pause your video here and just make sure that all of these steps make sense to you. Okay, I think I may have made one teeny tiny error. Well, actually, it's not a teeny tiny error. It's a quite substantial error when you consider your MIPS programs. Although I have my register map, I did not pay careful attention to it. So here, notice what I have done. I have obtained T0 as 4 times I, but then in order to compute the base plus offset, I'm using S4 register, which is I. So here, T0 is going to be 5 times I, which will be naturally a very small number. So this particular line would have given you a segmentation fault. So I'm glad that I made this mistake to teach you that such things can happen in your code. So let me fix this. Instead of S4, I should have used S3, which is the base address. So I'll use S3. Now T0 will be a proper memory address. Let's check it one more time. So T0 is S4, S4, then T0 is T0 plus T0, giving you 4 times I. 4 times I is added to the base address, which is at S3, and it is stored back in T0. Then you use the base as offset addressing method to get the value from that location, and you store the value, or rather you load the value into T1 from the main memory, and then you use T1 register to perform your computations, and you place the result back in S1, which is for G. Perfect. So this example is correct. Okay. Now, so far in our examples that I have covered, I have assumed that register somehow has obtained the base address of the array. Now, let me introduce you to the instruction that gets you the base address of an array. Not only the base address of an array, but address of any variable. And that instruction or that operation is load address. So load address has two arguments: the register where you would like to store the base address. Now this can be a user friendly address location friendly register, one of the S registers or T registers, a general purpose registers. That's the word that I was looking for. It's excuse me, it's going to be one of the general purpose registers, followed by the label inside of the main memory, where label is pointing to the address of, or the starting address of the memory. So let me repeat it one more time. Load address takes in two arguments. The first argument is going to be a general purpose register, followed by the label to the memory location whose address we would like to retrieve. Now this is an example of how you would load the address of the array, the base address, into the register S0. I can also load the addresses of simple variables inside of my memory. So let's say in your data section you have Z, which is dot word, let's say a value, let's say 5. If I were to do LA to $S1 comma Z, now S1 is going to have the address of Z. It's going to be a large value, a humongous value, because it's a memory address. If I were to do LW $S2 comma Z, however, S2 will store the value 5, because here we are loading the word from the memory location that is pointed to by Z. In this case, we are loading the address into S1 that your label is pointing to. So there's a difference. So make sure that you use the correct instruction. Okay, next I'm going to work on a full-fledged example, and I'll show you how to convert a C code to MIPS assembly, and I'm going to write a complete solution for this. So let me really quick obtain a copy of this code so that I can use it as a reference. And then I'm going to give you the solution. And in the meantime, you can start thinking about how to perform this in MIPS. All right, so let me give you the solution. Now, before I give you the solution, let me partition this into these three nice columns. Let's say that this space right here, these two spaces are more than sufficient. These two columns are more than sufficient for me. So I will have my data section right here. So I'm going to use the stub. So dot global main, telling the MIPS assembler that main is going to be a global function, followed by dot text, where most of my code is going to be placed, followed by the function label for the main. So main. In my dot data section, I need to declare the array because I'm declaring array of 10. So I need to declare that in the dot data section. So I'm going to perform array colon dot space 40, because I am declaring a space for 10 integers where each integer occupies 4 bytes. So I need to reserve a space equal to 40 bytes. Next, inside of my code, I set I to 0. So let me first create a nice register map. And I'm going to actively use this register map to guide me how to use different registers. So I will use S0 for the base address. I'm going to use S1 for counter I, the loop counter I. And I'm going to use T0 to store constant 10, because I need to perform a comparison between I and the constant value 10, and that has to be done using a register. So this is my register map, which I'm actively going to use. So first things first, let me obtain the base address. Load address into $S0 of array. So here S0 is address of the first element, address of array of 0. Now notice here that I'll try to comment each and every line of my MIPS code, because let's say in future I were to write a really huge code or a really long piece of code, then the comments that I have inserted for each line is going to be quite instructive for me should I run into some problems. Next, I'm going to set I to 0. So S1 has to be set to 0. I have not given you the LI instruction yet. LI stands for load immediate. So why don't I use the LI instruction here? So load immediate to $S1, comma 0. So I is equal to 0. So the instruction is LI, which stands for load immediate. Alternatively, I could have used an add-I instruction where I could have performed add-I to $S1, comma $0, comma 0. That would have accomplished the same task. I is set to 0 now. Next, I need to set up my for loop. So for. So I'm going to create a label called for. I will not execute the for loop should I be greater than or equal to 10. So let me set up the exit condition for the for loop. Branch if greater than, if I, which is S1, if it is greater than or equal to 10. Well, I don't have 10 in a register yet. First, let me get the value 10 inside of a register. And let me use the add instruction for that. So add I to $T0, $0, comma 10. So this is my constant 10. So coming back to the for loop, I am not going to execute the contents of the for loop if I is greater than or equal to 10. So branch if greater than or equal to, if I is greater than or equal to 10, which is in T0, I'm going to branch to outside for. Now I have created another label called outside for. I need to make sure that I define outside for in my program. Otherwise, my MIPS assembler is going to yell at me. So I've set up the exit condition. But let's say that if this condition is not true, this branching statement evaluates to false, then I'm going to execute the next instruction, which happens to be the body of the loop, where I am setting array of I to I. So first, I need to get the address of array of I, and then I'm going to use the base offset method of addressing to place the value I at array of I. So let me get the address of array of I. So S0 is the base address. First, I need to calculate the proper offset in bytes. So I'm going to use T1 register for that. I have several registers to spare. Add to T1, S1, comma S1. So here I have performed 2 times I. Pound is for comments. So remember that. I'll add T1 to itself and store the result back in T1. So now I have 4 times I. Next, I'm going to add to the base address the newly computed offset in bytes and place the target address back in T1. So now T1 holds the address of array of I. Next, I need to store I, which is in S1, to my target location. So I'm going to use the base offset addressing method to store the value I at location or at array of I. So store word. Next, I'm going to increment my for loop counter. So add I to $S1, $S1, comma 1. So here I have done I++. Next, I'm going to jump back to my for loop, jump back to for. My outside for label has to be defined. So let me define it here. So here I have outside for, where your program simply exits using li to $V0, comma 10. So that's the system call code to exit a MIPS code. And then I'm going to make a call to the system. So using syscall. So that is the complete solution for that example problem. Now, what I would like for you guys to do is carefully go through the solution and find if there are any bugs. If you find that there are some bugs, then please let me know, or you can put it in the comments section in YouTube. I think it's a good time for you guys to also start looking into different codes and try to find for any hidden bugs. Okay. Now, for this Canvas quiz, the last problem that you need to solve is problem number 5, where you need to write the complete full program here. So use the concepts that we have discussed in today's class, use base offset addressing methodology to convert this piece of code to a C program, or rather this C program to MIPS code. Okay, I will end this lecturette right here. So that brings us to the end of our MIPS discussion on memory fundamentals and how to access memory values. In my next lecturette, I'm going to discuss how to implement functions in MIPS.